সালাম আলাইকুম।
ওয়ালাইকুম সালাম। আলামিন, কেমন আছো ভাই?
একটু ভাইয়া ভালো আছেন?
ভালো ভালো। গুড মর্নিং, গুড আফটারনুন।
গুড আফটারনুন।
আচ্ছা, রেকর্ডিং স্টার্ট হয়ে গেছে এবং স্টুডেন্টরা জয়েন করলে ওদেরও সব দে শুড বি এবল টু জয়েন, কোনো অসুবিধার কথা নেই। এবং থ্যাংক ইউ ফার্স্ট অফ অল এই ইভেন্ট করার জন্য। খুবই ভালো হবে, আমরা খুবই এক্সাইটেড।
তো
আর
মনে
এমনি
হয়
প্রেজেন্টেশন ম্যাটেরিয়াল কি অনলাইনে পাওয়ার পয়েন্ট এরকম কিছু শেয়ার করবে?
হ্যাঁ হ্যাঁ, পাওয়ার পয়েন্ট প্লাস আমি কিছু অ্যানোটেট করার ট্রাই করবো হয়তো,
আচ্ছা,
বোঝানোর সুবিধার্থে।
ওকে, থ্যাংক ইউ। হ্যাঁ, আসসালামু আলাইকুম তাদেক ভাই।
ওয়ালাইকুম আসসালাম, কেমন আছো?
ভালো ভালো। আমাদের প্রেসিডেন্ট সাহেব চলে আসছেন। এখন তো আমরা গেস্টের জন্য অপেক্ষা আছি। হ্যাঁ, সেই।
স্টুডেন্ট কয়জন জয়েন করছে সেটা হলো কথা।
হ্যাঁ, এই যে কিছু জয়েন হচ্ছে আস্তে আস্তে আর কি।
আচ্ছা আচ্ছা।
ওকে, আমরা রেকর্ডিং এ শুরু হয়ে গেছে এবং ইনশাল্লাহ ভালো হবে। আমি ইয়ে করি। আচ্ছা, দেখা যাক একজন জয়েন করুক। আমাদের কি কোনো ইন্ট্রোডাকশন করার দরকার আছে নাকি আলামিন ক্যান স্টার্ট?
না, আমরা স্টুডেন্টদের সাথে ইন্ট্রোডাকশন করে তারপর স্টার্ট করি, কে কোথায়
ওকে,
পড়াশোনা করছে,
ঠিক আছে।
কোন গ্রেডে, নাম, এগুলো আর কি।
আচ্ছা, ওকে। আমি তাহলে একটু অডিও অফ মিউট রাখি।
জামশেদ, তুমি এমনি শুরু করবা? জাস্ট টু ওয়েলকাম এভরিওয়ান, অর আমি শুরু করব?
শিওর। হ্যাঁ, আপনিও করতে পারেন। ওকে, আমরা দুজনেই করবো না? এই,
হ্যাঁ হ্যাঁ,
আমরা
ঠিক
কি
আছে,
আর
জাস্ট
কতক্ষণ ওয়েট করব? 5 মিনিটস?
না, দুইটা তিন। লেটস ওয়েট ফর 3 মিনিটস।
3 মিনিটস, ওকে।
স্টুডেন্ট কেউ মনে হয় জয়েন করেনি, স্টুডেন্ট কি কেউ জয়েন করেছে? কাউকে তো দেখছি না।
আচ্ছা,
হ্যাঁ, ইসে জয়েন করছে, আমি দেখছি যে রেড ওয়ান জয়েন করছে। হাই রেড ওয়ান।
রেদওয়ান, জুনায়েদ দেখতেছি, আর একটা গুগল পিক্সেল, মেবি 3 অফ দেম।
আসসালামু আলাইকুম।
যে কি আবিরের জয়েন করার কথা আমি দেখে বলে আসতেছি।
ওকে।
তোমাদের ওদিকে গরম পড়ছে কেমন?
আমাদের গরম অত বেশি না, মানে 80s, ম্যাক্সিমাম 82-3 এরকম যায় আর কি দিনের বেলা।
ও
আবার
আচ্ছা,
রাত্রের
তাহলে
বেলা
তো
তো
হ্যাঁ হ্যাঁ,
ওরকম
মাছ মাছ
খারাপ না।
বেটার দেন আস।
এলের দিকে কি আরো গরম নাকি? কি অবস্থা আপনাদের?
হ্যাঁ হ্যাঁ, আমাদের কয়েকদিন ধরে ভালো গরম পড়ছে।
ও,
হ্যাঁ,
ভালো
মানে
তো।
দিনের বেলায় তো 90s,
ও আচ্ছা আচ্ছা।
90s ক্লোজ টু 100। হ্যাঁ,
10 ডিগ্রি কমায় বলেন কেন সাদিক ভাই?
না না, আমি বলতেছি ক্লোজ ক্লোজ টু 100, তোমার 90s থাকে। হ্যাঁ,
আচ্ছা,
মানে 100-এ উঠে আর কি, বাট 100-এ থাকে না, 100 তোমার ই আর কি।
ভাইরুল ভাই
বাট
শার্ট দেখে
ইটস
তো মনে
হট,
হচ্ছে ভালোই আছে। হ্যাঁ,
ইটস ভেরি হট। হ্যাঁ,
সেই।
গত
আপনারা
দুই
আসেন
তিন দিন
এদিকে।
যাবত হাইয়েস্ট 100+ আর কি।
আচ্ছা আচ্ছা, তাহলে এদিকে নর্থে চলে আসেন, আমাদের সাইড থেকে যান কিছু।
যেমন আজকে এখন কত টেম্পারেচার দেখি।
100-এর মতো মনে হয় আজকে এখন।
হ্যাঁ, এখন 100 এর মতো। হ্যাঁ, 100।
ও আচ্ছা আচ্ছা।
হ্যাঁ, আবির জয়েন করতেছে এখনই প্রায়।
ওকে, শিওর।
আমাদের স্টুডেন্ট আরো বেশি হওয়ার কথা না, 10-12 জনের মতো মনে হয় রেজিস্ট্রেশন হয়েছিল।
আমি তো দেখছিলাম 10 জন মতো রেজিস্ট্রেশনে।
আমরাই তো মনে হচ্ছে বেশি নাকি? বেশি।
তাই তো মনে হয়। আমি
হ্যাঁ,
দেখলাম
এখন আমি
10
একটা
জন।
জিনিস চিন্তা করতেছিলাম যে দুপুর 2টা শনিবারে, আমার কাছে তো মানে মনে হয়েছে ওকে টাইম। এখন আহ, কোনো টাইমই সবার জন্য পারফেক্ট হবে না, বাট দুপুর 2টা আমার কাছে মনে হয়েছে যে ইটস ম্যানেজেবল, শুড বি ম্যানেজেবল ইফ পিপল আর ইন্টারেস্টেড।
হুম,
আমরা শুরু করি, তারপরে দেখা যাক। এটা তো ফার্স্ট
হ্যাঁ,
টাইম সাদেক
ফার্স্ট।
ভাই। হ্যাঁ, উইয়ার জাস্ট স্টার্টিং যে আমাদের হার্ডওয়্যার ক্লাসেস, তো আমাদের মোটামুটি একটা আইডিয়া হবে হোয়াট ইন্টারেস্ট স্টুডেন্টস মোস্ট, তাই না? হোয়াট টাইম ইজ দ্য বেস্ট, দেন উই ক্যান গো ফ্রম দেয়ার। ইয়া।
আর
ঠিক
রেকর্ড
আছে।
তো থাকছেই।
জি।
হ্যাঁ হ্যাঁ, রেকর্ডিংও হচ্ছে। হ্যাঁ
জি,
হ্যাঁ।
দ্যাটস ট্রু, দ্যাটস ট্রু।
তো ঠিক আছে সবাই, ওয়েলকাম এভরিওয়ান টু আওয়ার ফার্স্ট এভার হার্ডওয়্যার ইঞ্জিনিয়ারিং ক্লাস। Big thanks to Aziza and Alamin, the two volunteer teachers. Big thanks to San Jose branch for allowing Southern California students to join. So yeah, please keep an open mind, ask questions. Good luck. I'll give it to Jamshed.
Oh, thank you. 1 second. I'm just looking to see if people joined. Add notification. Sorry, 1 second. Okay, save. Okay, let's start. I guess, thank you, everyone. Whoever's here or joined, we're recording this on video. Welcome to our hardware engineering course. This is our first ever hardware engineering class. We're super excited to have everyone. I think people are still joining, so that's great. We are part of the American Association of Bangladeshi Engineers and Architects, and we regularly arrange such events and sessions where we teach software, hardware, all kinds of engineering concepts to next generation students and also to professionals. So welcome. Hopefully you will reach out to us after the event to learn more about AABEA. So with that, I will transfer to Alamin, who's our amazing instructor for today. Thank you, Alamin, for being here. And yeah, let's start. Thanks.
Hello everyone, my name is Al Amin. Thank you so much, first of all, Jamshid Bhai and everyone for joining and introducing me. We'll introduce first every students and including me, and then we'll go to slide our main class. So from me, my name is Al Amin. So I did my bachelor's and master's in electrical engineering and PhD in material science engineering, and currently working as a process integration engineer at TDK Corporation. So I would request all the students, please introduce yourself, your name, and where are you currently studying. So that would be great to know everyone.
Hello, assalamu alaikum everyone.
Walaikum assalam.
Yeah, my name is Janat Hassan, and currently I'm a high schooler. So after this summer, I will be a junior, and then I go to the North High School, and then yeah, and then
Great.
yeah, and in my future, I want to learn like computer science will be my major.
Okay, that's great. And the next one, next student.
Assalamu alaikum everyone. My name is Ridwan Zaman. I'm a rising senior at Milpitas High School. And when I grow up, I hope to major in CS and get my MBA later down the road.
Oh, that sounds great. And how about the next one? Next student.
I think people are still joining. Maybe I see Nabil join.
I see the Abi Khan.
Oh,
He's
yeah.
Hi Abi, could you introduce yourself? Abir, Nabil, can you hear us?
Hello there.
Hi, can you hear us?
Yes, sir, I can hear you.
Okay, could you introduce yourself? Where you currently studying and your future goal, career goal?
All right. Hello, my name is Nabil, and I'm very interested in mechanical engineering, kinematics, things like that. Right now I just graduated high school at 16 years old at a valedictorian level. And my plan now is to maybe take 2 years in a community college and then go directly to a 4-year university, and then hopefully study my major in engineering, and more specifically mechanical engineering.
Okay, that's great. So we can start our class. Let's share my screen. Hello everyone, can you see my screen, like the presentations?
Yeah, we can see.
Okay, that's great. So I'll talk about the semiconductor materials device and fabrication. So as I introduced myself at the beginning, so let's deep dive. Um, so this chart basically showing the innovation trends in electronics from very beginning. It's 18th century, so we got the electricity, right? The age of electricity. And in mid of 19th century, 1947, the first transistor was innovated. And from starting there, we got a computer, smartphone in 2000th century, and then now we are at the age of artificial intelligence. So it's a huge revolution in electronics industry. So when I look at the first transistor, how it was looked like at beginning. So this is point contact transistor. Is first developed at Bell Laboratories by John Burden and Walter Bretton. It's 1947. So you see how big it was, and you can see it's still in their laboratories display. This was our first ever transistor. We can say this was the beginning of modern modern age, kind of modern technology. So now I will talk about the more advanced. We have the more advanced mobile phone, right? The iPhone 17 Pro. So in this iPhone 17 Pro, if you open up and you see the A19 Pro chip, so if you zoom in this chip, we can see under microscope the backside how it looks like. So many system on the chip, on a single chip. You see memory, processor, all are integrated, and this is the front side of the chip. So, are you interested to see this how this looks like inside? So the main building block of this chip is a transistor. So you can think about like a building. So the main block for building a big long building is the brick, right? So in semiconductor chip is basically the transistor. So you know how many transistors in this A19 chip? You will be amazed. It's 25 to 30 billion transistors. Can you imagine? This is kind of the size of the nail. So it's 25 to 30 billion transistors integrated on this single chip. It's developed by TSMC, Taiwan Semiconductor Manufacturing Company. So they build this 3 nanometer N3P process node. So if we look at the schematic, how the transistor looks like. So this is basically the nanosheet get all around transistor. And if you further cut the transistor and you see inside how it looks like, this will be how it looks like. And if you further zoom in to see which material is used to make this transistor, you see the silicon fin in the middle. And around the silicon fin, you see the hafnium oxide. It's called gate oxide materials. And then surrounding is titanium nitride. So we'll learn how from the beginning, we'll learn from very beginning of the semiconductor fundamentals to how we can make this transistor in practical. So we'll learn everything from the beginning. So are you all excited to learn? Let's go. So just to imagine how this 3 nanometer transistor, how tiny is this? I have put here comparison. You can see the human hair, how it looks like. So our human hair is 70 to 100 micrometer. So within the thickness of human hair, you can print thousands of transistors of this 3 nanometer node. So is it not amazing? It is definitely amazing. So technology is very great in this sense. So to better understand the IC, so I have divided this class into 4 modules basically. So first, we'll learn the semiconductor and its classification. Second, we'll learn the diode. Diode is very fundamental semiconductor device. So we'll try to learn what is diode and how it works. And then we'll go to the MOSFET. So MOSFET, metal oxide, semiconductor field effect transistor. This is the main building block, actually, main device for our chip. For example, I gave the example of A19 chip inside the iPhone 17 Pro. So then later on at the final, we'll learn how we can make this transistor in practical life. So let's first talk about the semiconductor. What is semiconductor? Basically, from this name itself, you can feel like what's semiconductor. Conductor is the material that's conduct the electricity, right? The semi is kind of half. So semiconductor materials, electrical conductivity is between the conductor and insulator. So conductor, you can say copper, insulator, glass, rubber. So the semiconductor materials conductivity is lower than copper and higher than insulator in the middle of this. So there are several semiconductor materials. So most used in our modern life, like in IC, integrated circuit, is silicon. So I have shown here, you can see the silicon electron configuration. So in a silicon, we have 14 electrons. So if you configure this 14 electron into different orbit, the first orbit has 2 electrons, and second orbit has 8 electrons, and the last orbit has 4 electrons. So the last orbit, this shell is basically called the valence shell, and the electron is called valence electron. So these 4 electrons is basically participate in bonding with other molecules to make compound materials and all other things. So if you give some energy, this energy could be any type of energy, heat or light. So for example, if we eliminate under light, right? If light energy is higher than this electron bond energy with its nucleus, right? So I would say like SI, the center is called nucleus. So that's basically the positive charge nucleus, and the electron has its negative charge. So it has some bonding energy, electron binding energy. So if the external energy is greater than this electron binding energy, it will get off from this silicon orbit, and you will get a hole here because electrons is emits get off from this orbital, and you create a hole. This empty space is basically called hole there. And to better understand like the difference between conductor, semiconductor, and insulator, I have shown here band structure, band diagram. So you can see the conductor has a valence band and the conduction band. So valence band is basically the energy band of the outermost shell here in this figure. Let me um, uh, get a pointer so you better understand. So you see this one, right? At this outermost shell is called, the energy of this shell is valence band energy. And when electron gets free of this valence outermost shell, that energy level is called conduction band energy level. So in conductor, basically this is overlaps. There is no gap between the conduction band and valence band in between these two. So that means in conductor, you already have so many free electrons to carry the current. So this is called conductor. And semiconductor, if you see this valence band and conduction band, you have some energy gap to it. For example, for the silicon semiconductor, it has 1.12 electron volt. So in 0 Kelvin temperatures, I mean, at absolute temperature, there is basically no electrons, free electrons in semiconductor materials to carry the current. So you have to add some external impurities, or you have to add energy to get the free electron. And insulator, you can see this gap is even more, is greater than 5 electron volts. So insulator doesn't have any free electrons. So basically that's why insulator cannot carry the current. So next, let's show how to create this annotation. Okay, this is a little bit trouble actually. If I do annotate, it will stay here on the screen. That's not good. If this class was live, it was great. Anyway. So the next, we'll learn more details about the semiconductor classification. So semiconductor is basically two types. We can say intrinsic, that's pure materials. I mean, there is nothing on it. It's called intrinsic semiconductor, and the second one is extrinsic semiconductor. So extrinsic semiconductor, when you dope with other materials, then, I mean, just for example, mix the silicon with boron or phosphorus, arsenic, mixing them together, it makes extrinsic semiconductor. And that's how you can control the conductivity of the semiconductor materials. So that's the beauty of this semiconductor materials. So if I see the pure silicon, the intrinsic, you can see the silicon, how they bonded together. In the previous slide, we saw that silicon has a 4 valence electron, this outermost shell. So these 4 electrons in a silicon lattice, they bond neighbor by another silicon atom um, with, and then make this kind of silicon crystal structure. So and it has very low conductivity because very few free electrons on it. So this extrinsic semiconductor can be classified into two types. One is P-type, another one is P-type semiconductor. So what is P-type semiconductor? So P-type is when you dope, I mean, mix another impurities with 3 valence electron. For example, boron, indium is called P-type semiconductor. So, for example, here you can see that I have added the boron inside the silicon. So boron has 3 electrons in its valence band, and in the outermost shell. So that 3 electron bond with three of silicon electron. So one bond to create one bond, you need two electrons. So this two electron bond together. Looking for some annotation. It is draw. Okay. Okay. So boron, you see, when boron is bonding with silicon, basically boron has an empty space here. So this empty space we call is holes. So in this p-type silicon, the majority carrier is hole. When as many as you want to dope the boron with silicon, you will have as many as a hole you can create. And the minority obviously will be some minority carrier electron. And the second type of extensive semiconductor is N-type semiconductor. So to make the N-type, you have to mix this silicon with pentavalent impurities, for example, phosphorus and arsenic. So in this example, you can see that phosphorus, right? So phosphorus has 15 atom in total. So the last shell, the outermost shell has 5 electrons. So out of this 5 electron, 4 electron bond with 4 of the silicon electron, and you have 1 extra electron here. So this extra electron is basically free to move inside this p-type silicon lattice, right? So as many as you dope this phosphorus with silicon, you can have much more free electron. So you can basically control the conductivity. If you have more electron, it will have more conductive, and less electron, less conductive. So basically, you can control the conductivity of this n-type silicon by
So,
controlling the
I
dose.
mean, one thing I wanted to ask, maybe it will be clear for everyone else also. So it's kind of like when we see like a lack of electron, that's a hole, right? And that's like more positive, and we are calling that a p-type, right? I mean,
Yeah.
okay. Is everything clear to everyone so far? Anybody has
So
question?
please ask question if you don't understand. I was like
Yeah.
looking for something to uh, if I had like blackboard or something, it would be much better to
No, I think that
explain
it's good.
this.
I
But
mean, you're doing good. Yeah.
uh,
Yeah. So
but if
just
I do,
stop us, like if you have question. Yeah.
yeah. So
Yeah.
the student, please, if you don't understand anything, any concept, please ask the question. So that's
Yeah.
just explain much more.
Thank you.
So yeah, so in this case, so we got at this point we got two type of semiconductor materials. Basically, for here in example silicon. So we got a p-type silicon. Inside this p-type silicon, what we have holes. So we can consider this equivalent to positive. So p-type is kind of positive. It has a positive charge in it, and N-type, you have electrons inside, free electrons. So it's basically, you can consider it's equivalent to negative charge. So let's go to the next slide. So now I will talk about the very basic semiconductor device as a diode. So in previous slide, we learned this p-type and n-type. Now we will learn how we can use this p and n-type silicon to make the diode. So let's see what's the diode first of all. So it's a semiconductor device. It's basically allow the current to flow in one direction. So this is the p-type and n-type we learned in the previous slide. So if you sandwich them together, uh, layer by layer, you can make a diode. And we can symbolize this diode as this kind of triangular shape. And so this broader triangle, this side is called anode. So the P side is called anode, is positive, and N side we call is cathode, is a negative side. And in real life example, for this diode, you can see this circuit is basically our car, the USB charging port. It has this SS32 diode. And another example, you can see this is basically the charger. Our charger, it has the Zener diode. There are many types of diode actually. So this Zener diode basically used for the reference voltage. And next slide, I'll talk about the diode working principle. So this is very important to understand. So when left side, this one, if I could draw, it's getting, let's try again. If I want to click, okay. So this is P region, right? So as I said, this P region basically has a positive holes in it, right? We have so many, this is basically positive holes, and other side is inside. So when you sandwich them together, for example, P type and then side by side N type, so it has first of all, the diffusion happens. From inside, it has an electron in the inside. These electrons goes to the P side region, and the holes, positive charge go to the inside region. A diffusion happens, and at the equilibrium state, since electron goes from N region to P region, you can get a positive charge here at the junction. There is junction level, you have the positive charge. And since holes, that means positive, is going to the N side, so you have basically the negative charge here at the junction. And we know that this is how it looks like. It looks like a battery, right? If we know battery has a parallel flat capacitor battery, so basically it has a positive charge, right? Positive charge and the negative charge. And the electric field basically works from the positive charge to negative charge. If you know how the electric force line works, basically from the positive charge, electric force line go out from the positive charge, and negative charge is go in. And that's how, if you place side by side, uh, positive charge and negative charge. So from positive charge, the electric force line go to the negative charge, and it basically attracts together. But if you place positive charge here, so this basically opposite directions, these force lines, so they basically repulse each other. So in this case, at this junction, you can see the positive and negative, right? So electric field is best from inside to the P side region. So in this forward bias, so when we connect this positive, this is a battery, positive and negative. So when we connect the P side with the positive terminal of the battery and N side of the negative terminal of the battery, what happens? So this one basically electric field works like this, right? If I say this one, and in the junction, electric field is this direction. So basically it's opposite. So if you apply the more voltage here in the battery, maybe if this diode is made of silicon, so you have to apply voltage greater than 0.7 volt, then basically you are closing the barrier, the potential barrier at the junction. And this is called forward bias. So basically then what will happen, electricity will flow, and you will see the light on this lamp, right? Any question from this student? This is very fundamental to understand the electronics device. So in future, if you want to study, you need to know this one. So
We are applying the positive voltage, basically, right?
yeah, but just applying the positive voltage here. So
Yeah.
if I say very simply, not go deeper. So when you P, that means positive. When you P side connect with the positive terminal and negative, N is negative, N is you connect with the negative terminal of the battery. This is called forward bias. And what happens? Basically, very simple. Positive terminal battery, that means you have positive charge here. So this positive charge basically will attract this negative electron in the N region. So electron basically will flow from this side to this side, right? That means you are getting electricity in simply, in simple way to understand this. And now let's talk about reverse bias. I have drawn so many annotation here.
I have a separate slide for the reverse bias, right?
Yeah.
Yeah.
So this is the reverse bias. So
Yeah.
reverse bias is just opposite. So basically in forward bias, we connected the P side with the positive terminal. Now we are connecting P side with the negative terminal. So what happens since this is negative? So you have a, oh, sorry, I made the annotation here. So basically what happens here, negative, that means we have negative charge here in the battery, right? So this negative and this side, as I said, it has so many holes. That means it's positive charge. This is a white circle. So it's this negative pull away this positive charge from this junction. So that means it increase the barrier in the junction. So that's what basically you will not have any current flow on this. But if you apply more voltage at certain point, it will break down the barrier, and you have huge current. That's called avalanche. So this is how the diode basically works in the forward bias and reverse bias. So now let's see the characteristics curve for this diode. So I have put here characteristic curve on the right side. So this connection, I have a question to the student. Are you listening? So could you tell me which is it forward bias or reverse bias, this diode connection? Hello?
Can you hear us?
Can you hear us?
What about Junaid? Hi, Junaid. I pick on you.
Hello. Yeah. I think it should be like a forward bias.
Yeah, great.
Good
Yeah,
job, Junaid. Yeah.
good job. Thank
Thank
you.
you so much.
Smart
Thank you. You're welcome.
mama. Yeah.
Yeah. So because this is forward bias, right? Now let's see if we increase the voltage of this bias, what happens to the current? So you see in this characteristics curve. So if this diode is made of silicon, so you have to apply voltage greater than 0.7 to flow the current. At very beginning, actually, we will have some current, very tiny bit in the graph you can see. So in the forward bias, you are increasing the voltage. At beginning, you have very little bit current, this leakage current. And after certain voltage, this is best for silicon is 0.7, for germanium is 0.3 volt. If it's greater than that, you will have the higher current flow through this circuit. And now let's apply the reverse bias. So I just changed the polarity of this battery. So this is the reverse bias. What happens in the reverse bias? You can see that in the reverse bias, in previous slide, as I explained, so the potential barrier increase, so you won't have a current flow. at the very beginning, you have some leakage current. Leakage current is always there. But after a certain voltage, if you increase the voltage at certain point, the potential, it will break down actually. So that's called the breakdown voltage, and you will have a huge current flow out through this diode. So if you further increase, it might get burned actually, because it will heat up this device. So this is how diode works, and in forward bias and then reverse bias. Now, next topic, I'll talk about the transistor. This is very exciting. So the MOSFET is metal oxide semiconductor field effect transistor. So let's see how it looks like. So this is the schematic. You can see we learned in the previous slide that we learned what is p-type silicon, what is n-type silicon. So in this MOSFET, you can see this is p-type and p-type silicon. On this p-type silicon, you have to create n or you have to dope the n-type this side to make it source, and another n-type, it's called drain and gate. So basically, this MOSFET diode had a 2-terminal, and MOSFET has 4-terminal, and this is gate, source, gate, and drain. So here, this source and drain, the distance between source and drain, we call is gate length, expressed as a L, and this width is called gate width. Basically, it's expressed as W. And now we'll learn how this MOSFET basically works. It's very interesting. I have simply drawn here the diagram in 2D fashion. So this is P, right? P silicon. So what is P-type silicon? In the first substrate. As I said, P-type silicon has holes in it, so many holes, and as a majority carrier, and electron as a minority carrier. And the left side, you can see this. This is source, so this is n-doped, so it's heavily n-doped. That's why it's called N plus. So it has so many electrons. And then right side is also n-doped. It has so many electrons. And we have an oxide here, oxide layer. And on top of that, we have a metal gate. So now we'll control the electricity from the source to drain by applying the voltage at the gate. So we are applying the voltage. So this is gate to source voltage, V plus. So you can see this is basically when you apply the positive voltage at the gate, I mean the metal gate, you have basically positive charge right here. So this positive charge, what it will do, it will attract the minority carrier, I mean electron, from the p-type silicon, right? So then this electron from p-type silicon, that's minority carrier, it will come and accumulate here at this and create a junction between, create a channel between the source and drain, right? And then what will happen? Since we have a positive voltage here, we'll have a current flow from right side to the left side. That means drain to the source. So in this case, so by controlling this gate voltage VGS, and you can control the current. If you apply more gate voltage, you will have the more current flow from drain to the source. And also, if you apply more VDS, you can Basically, this is to control knob. You can play with this to control this device. So in this device, MOSFET, since electron is carrying the current, so that's why it's, and basically throughout this N channel, that's why it's called N MOSFET. So we have another type of MOSFET as P MOSFET. In that case, if is the whole is contributing to the current, that's this called P-type MOSFET. So this is P MOSFET. It's just the opposite of N MOSFET. So in the N MOSFET, we had a N plus, but in P MOSFET, you can see here is P-type. We will have a P plus. So this is length and this is width, get length and get width. So I think this is my typo. Let me fix it. It should be P plus. So in this case, when you apply the negative voltage, you have to in the pre-MOSFET you have to apply negative gate voltage. You apply negative gate voltage, that means you are accumulating negative charge here. This negative charge will attract the holes from N silicon and it's accumulate near the junction, and it will create the P channel between the source left side and the right side is drain, source drain. And you will have a current flow from source to drain, right? Is it clear, Junaid?
Yes, sir. Of course.
Good.
Yeah,
So
there's other students like Nabil and Redwan. We are going to quiz you also, so pay attention. So one thing I wanted to say is like here for the gate length that we are talking about, that used to be like once upon a time that was like a process, right? You remember? But now we don't directly relate that to the process. For example, like, you know, Intel's 18 nanometer process or anything. But so just for them to understand, the students, like the gate length is important, right?
Yeah, it's very important.
Yeah, it's very
So
important. It can
basically,
relate to the process, right? Itself. So
device performance. So for
exactly.
example, I gave the example of the iPhone 17 Pro, right? That has 3 nanometer. So that's 3 nanometer is basically this gate length from source to
Exactly.
drain. Can you imagine how
How
narrow
small?
is this? How tiny is it?
Nanometer you were talking about.
Nanometer. So
Yeah.
this thousands of this like MOSFET can fit into the thickness of our hair. So this how tiny our technology right now in our
Right.
iPhone 17 Pro. So this is how basically the P MOSFET works. So you apply negative voltage and you attract the hole from this P silicon minority carrier and you create a channel and you get the current. And next, this is a MOSFET characteristics curve. So as I said here, that by controlling this gate voltage and drain to source voltage, you basically can control the current flow from drain to source. So this is how I have shown here in this diagram. So the current in the MOSFET is expressed by this equation. So in this equation, I will just say you can see four parameters. One is W. This W is basically the gate width, as I said, and L is the gate length. So by controlling this dimension, how bigger this gate length, gate width, you can basically control the current flow through this MOSFET device, right? And also get to source voltage and drain voltage. By controlling these two parameters, you can control the current inside this device. That's amazing. So in this graph, So you can see the y-axis is the current, that's drain current in this structure from drain to source, source to drain. That's the current ID. And x-axis is the voltage, drain to source voltage. So at certain point, uh, so there is another threshold voltage. For example, in the diode, if it's silicon diode, the threshold voltage is 0.7 volt, right? So in the same way, in the MOSFET, you have a threshold voltage. You have this gate voltage, you have to apply this gate voltage greater than a certain value. For example, it's basically depends on the device structure. So it's usually 0.7 to 1.2 volt. And currently gate all around, the nano ribbon FET is lower, the threshold voltage, around 0.3 volt to 0.5 volt. So you have to apply the gate voltage greater than that to make it work. So if you apply the gate voltage greater than the threshold voltage, and then you increase, so you basically made the channel active, and then you increase the drain to source voltage, you will have a higher current. As you go right side, you will have a higher current. At certain point, it will saturate. So the first region we call is linear region, and then second, when it gets saturated, the current, that means current doesn't increase anymore with increase in drain to source voltage. That region is called the saturation region. In this saturation region and the linear region, in our digital circuit, basically we operate this MOSFET in the linear region, and in amplifier and rectifier circuit we operate the MOSFET in the saturation region. So there are so many things to learn to talk about this, but it will be too many complicated. So I am just stopping here. Maybe in future class we can carry on from there. And so far we learned what is semiconductor materials and how the classification of it, and very basic device, diode and MOSFET, how the MOSFET looks like and how MOSFET works. Now we'll learn the fabrication. Fabrication means how you can make the transistor in practical life. In fab, it's called the foundry fab, where basically the transistor is made. So this diagram is very nice diagram. It basically tell you from the beginning. Basically, we use the sand, right? Silicon dioxide, and then we heat up, melt, and do refining. Seeding, growing, you get this silicon ingot, and from there you dice it, and after dicing it, you get this round shape, circular round shape. It's called silicon wafer, and you get a bare silicon wafer. For now you need to pattern, right? You need to pattern the device. You have to do the doping, and you have to create the gate oxide, all those things. So first we do the photolithography process, development process, then we do the etching process, stripping process, deposition, different material deposition. For example, for the gate oxide, we deposit silicon dioxide, hafnium oxide. Those are deposited by atomic layer deposition, ALD. So it's deposited by layer. So this is deposition process. And then we do the testing, right? Whether after making the chip, we test it, whether it works for the purpose we made the device. If it's confirmed that it's working, then we dice it into single die, and then that die we do the packaging. After the packaging, we got this final device. For example, as you saw, the iPhone 17 Pro, A19 Pro chip. So this is the final. So we started from silicon sand, and then we finished to get full finished integrated circuit. We call it chip. And now I'll go details, this IC fabrication. This is interesting. Please pay attention how we'll try to make N MOSFET here and how the process basically works step by step. So at beginning, here is like this silicon wafer. I have drawn here in 2D structure. So at beginning, we take this P-type silicon wafer, and on top of this, we coat photoresist materials. So photoresist materials, this yellow color I have shown here, this is basically photosensitive materials. So this photoresist material has different type, negative, positive. So if it's positive photoresist, so that's basically if you expose under light at certain wavelength of the light, these materials respond to the light. And inside this material, the chemical bonding breaks. The area gets exposed to the light. So we took a silicon wafer, then we poured this photoresist, and then we have to photomask. We have to set the photomask. So in this case, you see the open side, the light will pass through this open side, and there's the black one is basically will block the light. So here you can see this called photolithography process. So in photolithography process, basically what happens, you just expose this wafer under a light at certain wavelength. So when you expose, what happens? So this area is getting exposed. So in these photoresist materials, the chemical bonding breaks, and you can basically remove by doing the development process. So the fifth state is the development process. So it's basically immerse this whole wafer inside the developer chemicals, and you remove this photoresist. So another thing is the photoresist that wasn't exposed under the light, I mean this area, so it becomes hard. That's interesting. So the area that get exposed, it gets soft, and you can easily remove by immersing into certain chemicals. But the area that is not exposed, it gets hard. And second, so from the previous step after the development, what we got this structure, right? We started with the P silicon, right? And then after photolithography process and development, we got this structure. Now we need to do doping, right? We need to create this left side N plus and in N type, and the right side is also N plus. So what do we do? This process is called ion implantation. So basically you expose this wafer under the ion beam. So we use phosphine for the phosphine gas for the phosphorus doping. So as I said in the doping slide, if you dope phosphorus with silicon, phosphorus has 5 electrons, creates an N type. So you will have this N plus region after this ion implantation under this phosphorus ion beam. So you have left side N plus, right side N plus. And now what we have to do, we don't need this photoresist anymore, right? There is no function of this photoresist. We have to remove from the top of the wafer. So this removal process, we call it stripping, lift off process. Basically, we lift off the photoresist from the top of the wafers. And then what we got, we basically got this structure. We have a we took this P-type silicon wafer, and then we ion implanted this phosphorus to make left side N plus and the right side N plus N region. Now to make the MOSFET, we have to deposit the oxide, right? Because it's metal oxide semiconductor. So we have to create this deposit this oxide. So right now we use the silicon dioxide and hafnium oxide, gate oxide. And then another process is to deposit the gate. I haven't shown here all details like masking. It will take so many slides to understand. So simply you have to mask this N region and left side and right side to deposit this gate oxide and also metal gate. After the metal gate, we have to deposit this source and drain contact to make the connection to the external circuit, right? So we deposit this metal contact. Now we got a full complete MOSFET, right? Any questions so far? How we made this MOSFET?
So, I mean, when we are talking about the photoresist, right? So in general, we are talking about the positive photoresist, is it, or negative?
It depends on which pattern you are trying to make. So here I gave example for the positive photoresist.
Right. So the difference is that whenever they're exposed, that area is the one basically you are covering, right?
Yeah, right. So in the negative resist, the exposed area gets harder.
Right.
And unexposed area gets softer. You can develop array in the developer. But positive resist is like kind of opposite.
Yeah.
Wherever you are exposing, that area gets softer and you can remove easily.
Right. Okay.
So far so good. Okay, we are almost at the end of the class. So at end of the class, I want to show you something. This is Intel process technology. So last 20 years development. You can see starting from 19 nanometer. So this 19 nanometer is gate length, as you see in the previous slide I showed. So from the 19 nanometer, we got 65, 45, we're narrowing down. You see the corresponding figure. I mean, the ACM cross section, how it's getting narrower, 20 nanometer, 14 nanometer, 10 nanometer. Right now, we got 4 nanometer. Then the next area is angstrom area. Right now, Intel is trying 18 angstrom. I think it's in high volume manufacturing, and they are targeting 14 angstrom by 2028. It's getting smaller and smaller and smaller, the transistor, and our device performance is getting higher, right? Since we are in an AI area, we need high speed device. So you have to print as many as transistor to make work done, the computational work. And finally, this is the final slide, is semiconductor supply chain, how this whole process, this is too many complicated supply chain actually process. So here you can see the left, ASML. ASML is the leader in the photolithography process. So they make the photolithography tools and supply. So they're the leaders. And there are also other company, Applied Materials, Lam Research, KLA. So these companies, they basically make the equipment to process, to make the transistor. They build the equipment and sell to the fab. I mean the foundry company. For the foundry company, we have Intel, Samsung, TSMC. TSMC, they are pure play, so they basically pure foundry. Intel, Samsung, they do design and also they make the device. They do the fabrication. They are called IDM. And also we have we have to do the design, right? Who is going to do the design? So we have separate companies, Synopsys, Cadence, so they do the EDA, electronic design automation. They sell the software to design the circuit, the VLSI circuit. And we also have separate, this is a software company who sell the software to the design. And we have NVIDIA, Broadcom, Qualcomm. These are fabless manufacturer. I think Broadcom has fab, but NVIDIA, Qualcomm, they don't have fab. So they do the design. So they buy the software from these companies, Synopsys, Cadence, and they make the design of their circuit, and they get the print of that circuit, the printing of the circuit from the TSMC or Samsung, Intel, this company. So this is the overall supply chain for this semiconductor industry. So that's all so far for this class. Thank you so much. If you have any question, anything, please let me know. I'll be happy to.
Thank you. I mean, it was good presentation. Any question from our students?
I don't have a question, but yeah, I just want to say thank you so much, for sharing the amazing information to us, and it was great.
Yeah, thank you.
Yeah.
We have one more class tomorrow on the microelectronics. I will teach that from same time 2 to 3 tomorrow. So thank you,
Awesome.
everyone, Ridwan, Nabil, everyone who joined. Yeah, and thank you, our Southern California people, Mainul Bhai here, and I don't know who else is here. Jamshid Bhai, thank you. Jamshid Bhai is still here. Where is he? Yeah, so yeah, thanks everyone. And I mean, it was good. Yeah, it was a good presentation.
I tried to make it very simple so everybody understand, but it would be better if I could have some drawing board to draw and explain much more details.
Yeah, in the fall, maybe, we can do something. That's what we were talking about, Jamshid Bhai, Mainul Bhai, and everyone, that we can maybe do something, some face-to-face, some online, right? We can do both maybe in fall. Yeah.
No, thank you. I really learned. I mean, I used to work for Intel, but now I've relearned all of this. So thank you, Alameen. Thank you to everyone for being here. And then we'll see you tomorrow at 2 p.m. Right?
Thank you very much. Yeah.
Bye.
Thank you. Thank you, everyone. Bye.
Thank you. Bye.
Bye.